Video is a continuation of the live lecture we had. You can check the link to that video, the description of this video, and then search the channel under live, the latest live video. You see it, Inferential Statistics, and calculate some test statistics with worked examples. We have used chi-squared, we have used z-test. Now we want to continue with this lecture, and we are dealing with another test statistics. Now let me also mention that we mention ANOVA. We are going to speak briefly on ANOVA, but we are not going to use an example because it's going to be a very long calculation. But we want to know what or where is ANOVA applicable. ANOVA simply means analysis of variance. Analysis of variance. The one way ANOVA is used to determine whether there are any significant difference between the means of 3 or more independent or unrelated groups. For example, you have a first set of data and you want to check whether there's a major or significant differences between their means. You can apply ANOVA. Other tests such as the t-test or f-test can actually do this for only 2 sets of data. They cannot do more than that. But ANOVA can go from 3, 4, 5, 6 or higher to test for significant difference between the means of data. Okay. Now we want to also explain that ANOVA is a f-test developed by Fisher, and then it's going to have, depending on how many significant tests you're carrying out, you're going to have one null hypothesis and more alternative hypothesis. You can have more than one alternative hypothesis depending on what you are testing for. But we have at least one alternative hypothesis. Then you can have 2 or 3 or more. That is an ANOVA test for you. But you can also use it for only 2 sets of variables. And do more than 2. That's the beauty. So for the ANOVA, we can have the fundamental hypothesis written in this manner, as you can see on the screen. H naught such that mu1 is equal to mu2 is equal to mu3 is equal to dot 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 is equal to mu k. What is he saying? That there's no significant difference between the mean of the various set of data for data 1, data 2, data 3, up to data k sets, depending on what you have. And then mu is a group mean, and k is the number of groups. So after that, we can now state alternative hypotheses, whether for one alternative or 2 or more alternatives. That is what ANOVA is good at. So it's a superior test statistics that can test more than 2 sets of variables at the same time by comparing their means. So that is the beauty of it. So we are going to skip the work example of ANOVA here because of the length of time it will take to actually finish up that calculation. It's going to be so long. So I'm going on now to t-test. So t-test is also referred to as student t-test. Student t-test. It is developed by someone that doesn't want his name to be known. That's why they call himself students. Doesn't want to publicize his own name at the time because he was working for another company. So by the time he was bringing out the test, he didn't want his name to be known, to be attributed to him, because he doesn't have the right to do so based on the rules and regulations at the company where he was working. So he used the pseudonym students. So he was the one that developed student t-test. Okay. All right. So we want to go on now to t-test. So t-test is applied to compare the means of two samples, only two samples or treatments. That is two sets of variables. T-test is used for only two variables, two treatments, to check whether there's a significant difference between their means. So we need to use a standard deviation, the values, and then we have the t-test formula as we have on the screen here. T equals x1 bar minus x2 bar divided by square root of s1 squared over n1, s2 squared over n2, and the s itself is given as summation xi minus x1 bar all squared plus summation xi minus x2 bar all squared. Everything divided by n1 plus n2 minus 2. And those parameters, they are defined this way. Xi is each data set in the set. So we can have x1, x2, x3, x4, and so on. That is a small letter x. Then x1 bar is the mean of the measurement of the first set of variables, that is first sample size. So we have the first sample size mean as x1 bar. Likewise, x2 bar is the second sample size mean, second sample mean. And the size of a first sample is n1, the size of a second sample is n2. All right. Now, we have S1 squared and S2 squared as the variances of samples 1 and 2. And then the term in the denominator, we can replace it by pool variance as we have here. Pool estimate of variance, S squared equals N1 minus 1 multiplied by S1 squared. N2 minus 1 multiplied by S2 squared divided by N1 plus N2 minus 2. So that T formula can be T equals X1 bar minus X2 bar divided by square root of S square over N1 plus S square over N2. N1 plus N2 minus 2 is equal to freedom. Remember, we will need degree of freedom to check the tabulated values for the analysis carried out, the test statistic used. So we need the significant level, that is alpha. We also need degree of freedom to check the values. And the procedure to follow to calculate a t-test is this. We construct hypothesis first, then we go ahead, calculate the data. For example, we calculate the data mean for the first set of data, mean for the second set of data, calculate the variances, then calculate the pool estimate of variance, and use those items to calculate the t-value. After getting the t-value, we want to check the table value. We check the table value against the calculated value, then we make our conclusion. Now, if we use 0.05 as significant level, then we will check whatever we have on the table. If the table is higher or less, help us to make a decision. And let's look at the first example of this t-test. We have the example here. Suppose that a student in food science and technology department measured the biomass in milligrams produced by bacterium A and bacterium B in a shaped flask containing glucose as substrate. He had 4 replicate flasks of each bacterium as given in the following table. Will it be correct if he concludes that bacterium A produces significantly more biomass than bacterium B when grown on glucose? So we have the table here. We have group of values. We have bacterium A and bacterium B. And this was carried out 4 times, replicate 1, replicate 2, replicate 3, replicate 4. So we have the solution. The samples, H naught, the samples of treatments do not differ. That is the hypothesis. Formulate the hypothesis first. That samples of bacterium A and bacterium B, they are not significantly different. Even though when you look at this table, you see that the values are not the same. It appears bacterium A are always higher than bacterium B. But we will not go ahead and make decision based on that. So we cannot make a decision straight by merely looking at the values on the table. We subject the data sets to statistical analysis, then we make an informed decision, conclusion based on what we obtain. Okay, so now we start by calculating the mean for the data set A, and then calculate the mean for data set B. That's what we do now. For data set A, x1 bar equals 520 plus 460 plus 500 plus 470 divided by 4. And the answer is 487.5. Similarly, for x2, we add all these up. We get this answer, 7.5 as the mean. Then we calculate the variance of each set. The variance is calculated here to actually see what is being done. I put the formula down here. Here is the formula. Here is the formula. Variance s squared equals summation xi minus x1 bar, all brackets squared, divided by n1 minus 1. That's what we have here. So xi represents the data set, each data set value, like 520, 460, 500, and 470. And they are here. And the x1 bar is equal to this. So we substitute all that for all the values of this data. So when we carry out that s1 squared, we obtain 758.34. Then we do the same thing for the second set of value using x2 bar also. Then we obtain 491.66. Now that is variance for the two sets. Then we calculate the pool estimate of variance, as here is the formula. So we need variance 1 and variance 2. Variance 2, and then we need number of items in each variable of interest. We have there as 4. So when we substitute that into the formula, we have this full estimate of variance s squared. 4 minus 1 multiplied by 758.34 plus 4 minus 1 times 491.66, everything divided by 4 plus 4 minus 2. The answer is 625. So now we can now go ahead and calculate the t value. The t is equal to x1 bar minus x2 bar divided by square root of s squared over n1 plus square root of s2 over n2. When substituting all this, we come out with this. We come out with 13.01 when we substitute all the values. Now, mark you, we can get this one to be negative also. For instance, if x1 is less than x2, we can actually get what is here, the answer here as negative. It doesn't mean anything, it doesn't make any difference. Okay. Now, having got that, we need to check the value of the table, on the table, t value. So we want to use 5% significant level, and then the degree of freedom is calculated as this, n1 plus n2 minus 2. If we go to the table, the statistical table, then we can see what that is. Let's quickly check that on the statistical table. The statistical table is somewhere here. Okay, so we have this. We have the table here. The degree of freedom is 8 minus 2, 6. The degree of freedom is 6, so we are looking at this row here. And then for 5%, okay, since we are looking at a 2-day test, so we for 5% 2-day test, you can see it, 2-tail is up here. Then when you check that one to trace it to row 6, we have 2.447. That is it. That's the tabulated value. That is the value obtained from table. We are going to compare it with what we have calculated. Let's see what we have calculated. We have calculated 14.01, and from the table we got 2.447. 447. So for that we can make a conclusion. Our calculated t value exceeds the tabulated value. So that means there's a major difference, significant difference between the means. In that case, we will reject the null hypothesis and accept the alternative hypothesis, because what we calculated is higher than what is obtained from the table, from the t table. So we reject the null hypothesis and accept the alternative hypothesis. As that's a straightforward conclusion. And that is how t-test is applied. The student t-test is applied in a statistical analysis. Now, quickly we move on to the f-test. F-test is also used to check whether there's any significant difference between two sample variances. It is used to test if the variance of two populations are equal or not. And then it can also be two-tailed test or one-tailed test. The two-tailed test is checking against the alternative that the variances are not equal. The null hypothesis is saying that the variances are the same, but the alternative hypothesis holds that there will be a significant difference between the two set of values, the variances of two set of values. So this is the test statistic. F test is equal to S1 squared over S2 squared, where S1 and S2 squared are the sample variances. So the more the ratio deviates from 1, the stronger the evidence for unequal population variance. So we see how the formula for variance here. That's what we utilize. Xi is each data set in the set. X1 bar is equal to the mean of measurements in the first sample, and any is total number of data in the set. Now here, the degree of freedoms, we have 2 degrees of freedom that we are going to utilize to check the value from tables. The first degree of freedom is n1 minus 1, and the second one is n2 minus 1. So the way it is, we can employ this test for unequal data sets. Likewise, the test 2 that we earlier completed, we can use it to test for significant difference between a set of values that are unequal in number. Use it. All right. Now let's go and check the worked example on the f-test as well. This is an example right here. The researcher wishes to investigate the effects of replacing sand with laterite up to 50% in concrete. Concrete cube strengths were measured after 7 days for standard aggregate mix, and aggregate with laterite replacing sand up to 50%. And this was replicated 6 times. And the table below gives us the data. So I'm employing f-test with a alpha of 0.05, that is 5%. We want to know whether there's any significant difference between the standard concrete aggregate and the concrete aggregate with sand replacing laterites up to 50%. Sorry, laterites replacing sand. So we have 2 sets of replicates as seen on the table. Now, to begin, we will state the hypothesis. The null hypothesis states that the variances of both samples are not significantly different. And the alternative hypothesis says that there is a significant difference between the 2 variances. So we want to balance it now by checking with the test. So we have the variance formula up here. So we calculate variance for the 2 sets. And then the first part is to calculate the mean for each set of value. The mean is this: 14.61 plus 14.93 plus 15.004 plus 14.34 plus 14.52. Everything divided by their number 6. And the answer is 14.66. Likewise, if you do that one for the second set of value, that is x2 bar, we come out with 11.71. Now we use this mean to determine the variance for each set. When you substitute the value of mean with each data set, each value on the data set, then we can calculate the variance as we have it. So variance for group 1 is 0.06388, and for group 2, 0.7838, as you can see on this screen. Then we compute our f value as f equals s1 squared divided by s2 squared. And the answer is this, 0.06388 divided by 0.07838. The answer is 0.815. Now, the degrees of freedom for the two sets, n1 minus 1 is equal to 6 minus 1, that's 5. And n2 minus 1 also is equal to 6 minus 1, that's also 5. So, now I want to check from table under the F table for significance using alpha of 0.05. So our calculated value is 0.815. We are going to check the table now for F to know whether we are going to have a significance or not. So this is a F table, and V here represents degrees of freedom, and we have V1 and we have V2. So V1 is a degree of freedom 1 and V2 degree of freedom 2. So we can now go ahead. Now V1 is 5 and V2 is 5. So we check both of them where they link up. That is column 5 and row 5. Check column 5 up to row 5, and you see that the table value here is 5.05. Here we use degrees of freedom for rows and column to get the value of the F distribution significance level. So for table value we have 5.05. Okay. So we can see we obtain 5.05 from the table. Our own calculated value is 0.815. So our calculated value is less than the tabulated value. For that reason, we accept null hypothesis because calculated value is less than table value. So table value is taking precedence now. It's helping us to decide whether there's any significance in the differences between the two variances. So here we see that there's no significant difference according to 5% F distribution that we check. So that is it. So we make a conclusion that we reject the null hypothesis and then accept the alternative hypothesis. And what does that mean? It means there is no significant difference between the concrete strengths when cement is replaced with laterite up to 50%. So that is what we have. So that is the conclusion, and we have come to the end of the statistical test for inferential statistics that we have handled today. So I encourage you to like and share the video. Do not hesitate to subscribe to the channel if you haven't done so. So like the video and share it with other friends in other groups so that they can also watch the video and get the points that I share. So I want to see you in my next video. Say bye bye.